Before I begin, I want to thank Toto16 on GitHub for helping me get this project up and running on other platforms. Turns out when you only test a project on one computer, there's chances that, it won't work on others. So thanks to his help, I have been able to get this project running, and he's also contributed a bunch of fixes and improvements, such as, for example, continuous integration, so that the project automatically builds the latest version when there's a change on the main branch. I don't know if this is accessible to everybody, but it should allow you to run the project without needing to compile it yourself. Also, before we talk about input, which is the topic of today's video, we're going to talk a little bit more about context switching because I left this part out of last week's video, and I left a comment, but I did say I wanted to add it to this video because it is important. And it's the fact that I talked about a saved program status register and the exception link register, which store what the previous status register was before we entered the exception whenever we're context switching, and also the previous program counter, or where we were before the exception happened. The real registers that the CPU relies on to know the current exception level is actually the current program status register, and of course the program counter to know where we're currently executing. So when our process is running, the current privilege level is stored in the CPSR, and the current instruction is stored in the program counter, or PC. Then when we enter the exception, either through a syscall or through context switching due to switching processes, then those get stored in the SPSR and in the ELR. But once we're done with the exception and we need to return, we have a special instruction called ERET, or return from exception, which will return the program counter back to the value that's currently in ELR, and the current program status register back to the value that is currently in the saved program status register. So when we're in an exception and we're doing context switching, we don't interact directly with the CPSR or with the PC. We interact with the saved register and the link register, and then those get stored automatically into the correct ones when we return from the exception. With that out of the way, we can finally talk about input. So in order to have input in our system, we're going to want to work with a keyboard. Eventually, we're going to want to work with a mouse, but for now, it's just a keyboard. And that keyboard is probably going to be connected through USB. Now, the thing about USB is it's a pretty complex standard, and there are controllers that we use in order to connect to USB devices and talk to them. The controller that we're going to be using is the Extensible Host Controller Interface, or XHCI. Through this controller, we will be able to connect USB devices to our system, detect them, communicate with them, get the input from them, and all those things. Now, the thing about XHCI is it's a pretty complex standard, and that's just for the controller itself. Then USB itself has multiple versions. It goes up to USB 4, which I didn't even know existed just yet. And each of these and the controller itself have specs that are over 600 pages each. So we'll probably, as always, make a minimal version of a controller that can just do what we need it to do for the time being and expand it as needed. Also, a lot of the knowledge that I got for making this comes from tutorials made by a YouTube channel called Flare Coding. This was originally posted on the OSDev subreddit, and then of course on this YouTube channel and their GitHub. So most of the information that I am mentioning is actually covered in this channel. I do encourage you to go check it out because this is where I got most of my information, and it's much more in depth than the information that I'm gonna provide. At the same time, the series of tutorials is technically not finished. It definitely wasn't when I was implementing this, and I don't think it is even now that I'm writing this video, but the GitHub should be 1 or 2 steps ahead of the videos, so you can use that as reference. And I believe somewhere else on their GitHub, there's also a full implementation of an XHCI controller for an operating system, which I also used as reference a lot of times. Okay, let's get started. We're going to be using the QEMU XHCI device, which, even though the name doesn't explicitly say it, is a PCI device. So we've already talked plenty about PCI and how to implement a device with PCI and how to discover them and configure them, so we don't really have to do that. Now, for the most part, we've talked about VirtIO devices, but this is not one of those, but still the PCI part is exactly the same. This device then uses operational registers. They are a series of registers that we're going to be using to communicate with this device. The ones we care about are the USB command register, the USB status register, which we will use to send commands and read back the status of the device, respectively. The DNCTRL, or device notification control, the CRCR, or the command ring. And finally, the DCBAAP, which even just the initials is a mouthful. It's the device context-based address array pointer. Whew, that's a lot. We will see what each of these mean in a minute. Now, the way to initialize the device is, first off, we're going to write a 0 to the USB command, which should stop the device. Now, most likely we will be booting when we're doing this, so we don't assume the device is going to be running, but just in case, this is how we're supposed to do it. After that, we will write a 1 to it, which will tell us to reset. And at this point, we have to check bit 11 of the status. It will be a 1, and we have to wait until it becomes a 0. At this point, we want to start looking at other registers called the capabilities registers, and they look like this, but there's a lot of information in them, and technically each of them actually contains more information packed in it, but we care specifically about the HCS params 2, which contains two values that we care about: the ERST max, or the event ring segment table maximum, and the scratchpad count. And then from HCS params 1, we want to look at the maximum number of devices that are allowed on this controller, and the maximum number of ports. Now, this is a lot of information and it doesn't really mean a whole lot if we don't explain it, so let's go over it little by little. So we're going to start with the command ring. Just like we did with the GPU, everything that we've just done with writing a 0 and then a 1 and expecting a bit to be cleared is just to initialize the device, to start it up. But once the device is actually configured, we need to be able to send commands to it. We're going to be doing that through the command ring. And the command ring control simply indicates where that command ring is located in memory. So we're going to have to allocate some memory for this command ring and write it here. Then we want to look at the event ring. Just like we want to send the device commands, the device wants to tell us events that have happened, and that's what the event ring is for. Now, the ERST max register that I mentioned does not contain a pointer to that event ring. It simply indicates how many entries there can be into a table that indicates where that pointer is. I know that sounds a little bit complicated, but essentially, we're not going to define the event ring directly. We're instead going to define a table in which an entry defines the event ring. And this simply indicates how many entries that table can have. I think it's 1 in most implementations of XHCI, so really there's just 1, but just in case we're supposed to read it from this value. And then we're going to have to create this table, and there we're going to define where the event ring is, which we'll also have to allocate. Then there's the DCBAAP, which is the device context-based address array pointer. This is again another table that contains pointers to each device context. Now, each device that we connect through USB needs to have some information about it, and this is the context that we're talking about. So in this table, we simply will find a pointer to that context. So this is just a table with pointers to those contexts for each of the devices that are connected. And it also contains a scratchpad, which is the scratchpad count that we care about. I'm not entirely sure what the scratchpad is used for because the scratchpad count is actually 0 on QEMU XHCI. So I didn't really use it, but technically the first entries of the DCBAAP are the scratchpad. Okay, so we'll need to create a command ring, we'll need to create an event ring, we will write commands to the command ring, we will read responses back into the event ring, and we will read information about devices from the DCBAAP. But let's look at how these rings are actually structured. So the command ring and the event ring, they work somewhat similar to the vert queues that I mentioned in the last episode and in the first episode, but they're rings specifically. They're meant to be circular. Eventually, there will be so many commands and so many events that you will run out of space. So to fix that, the last bit of these commands and events is a cycle bit. It indicates the validity of the current event or command, and it changes. Once we reach a full iteration around the ring, it goes from a 1 to a 0. So let me explain how this works. When we begin, we count valid entries as the ones that have a 1 in this bit that we just talked about. So both the device and us are going to be able to go through the command ring and through the event ring. And once we find an entry that has a 0 in this cycle bit, then we will know that that entry is no longer valid. We've read all the valid entries so far. But once we reach the end of one of these rings and we need to loop around, what we're going to do is we're going to switch the value that we look for. Whereas before we considered 1 to be a valid entry, now we consider 0 to be a valid entry. Because all the entries that are written there right now that are no longer relevant because they've already been processed have a 1. And new entries are going to have a 0. And now we're going to read until we find a 1, at which point we know that we've read all the valid entries. And technically both our operating system driver and the device itself are going to be doing these reading operations and expecting bits to be 0s or 1s depending on the current cycle. So in order to keep that synchronized, in the last command of the command ring, we will write a special command that tells the device to toggle the cycle bit, essentially to stop looking for 1s and start looking for 0s. So all that we've talked about so far is how to communicate with the XHCI controller. But of course, besides communicating with the controller directly, we'll also want to be able to communicate with the devices that are connected via USB. And so we're also going to have some device transfer rings. They work similar to the command ring in that we'll be able to send commands there, and they will also use the same cycle bits in the same way that the other two structures that I just mentioned use them. But we will be using them to send commands directly to the device. And actually, devices are then further subdivided into endpoints, because they can have technically multiple functionalities, and we want to address each of those functionalities directly. So there's even more rings that we can use to communicate directly with those endpoints, but we'll get to that. Before we can actually start sending these commands and receiving events and all that, we need to talk about interrupts. Interrupts are crucial to the XHCI controller because they will help us know when something new has happened, such as, for example, a port change, that is, a device was connected or disconnected, as well as knowing when a device has new data for us, such as, for example, a keystroke. So in order to do that, we're going to want to use interrupts. Now, this is where the event ring segment table comes in. Like I mentioned before, this is how we set up the event ring. Whereas for the control ring, all we did was just allocate some memory and then write a pointer to one of the registers for the XHCI controller. This time we have to write a table. But like I said, it's a table with literally just one entry in most cases, I believe, but definitely in our case. And the table is going to look like this. It's going to have a pointer to the event ring and the size of the event ring, which if I'm not mistaken, I have hard-coded to be 512 events. So this is where we will allocate some space for the event ring and then write the pointer to the event ring. But in order to actually notify the device of this, we'll also want to set up an interrupter. And that's what the interrupter registers are for. They look something like this. First is the interrupter manager, or IMAN, then the interrupter moderation, or IMOD. Then we have the event ring segment table size, which just tells us how many entries are actually in our event ring. Then the event ring segment table base address, which indicates where the event ring table starts. And finally, the event ring DQ pointer, which is not necessarily a pointer to the event ring, but rather a pointer to the last event that has been processed. So the ERSTBA is the base address for the table. This is where the device is going to be able to go look for the table and process it. And then the ERDP is again going to point us not to the event ring itself, but to the last event that has been processed in the event ring. So we can write those values, but then we also need to do a little bit more configuration. First off, we need to enable interrupts. We do this by writing a 1 to bit 1 of the interrupt manager. Now keep in mind this is the second bit because the first bit is actually bit 0. That way we will enable interrupts. After that, we want to also enable interrupts by writing a 1 to the third bit of the USB status. And finally, we'll also want to write a 1 to the first bit of the interrupt manager in order to clear any pending interrupts that came before. So just resetting the interrupts just in case. So now we've configured the device to use interrupts, but we haven't actually defined an IRQ line, which I talked about in the last episode. In the last episode, we used interrupts to be triggered when a timer ran and reached its target. But in that case, we used a hard-coded IRQ line, 30, because that's the one that's used for timers. But in this case, there isn't a hard-coded one. And we're actually going to use a protocol called MSIX. MSI stands for Message Signaled Interrupts, and MSIX is just the extended version of this. It's just a more advanced way of sending interrupts. To be completely honest, I don't fully understand how it works. I just know how to configure it, and that XHCI relies on it. And the way that it works is we're going to write a table. In this table, we will define which IRQ line we want to use, which in my case I went for line 31, and then which address of the GIC we want to send this interrupt to. So this is just a more advanced and more complex way of implementing interrupts with a specific IRQ line that we can define at runtime. And finally, before we move on, I want to talk about the structure that we use in order to send commands and receive events, and that is the transfer request block, or TRB. Now, the transfer request block looks like this, although technically the control changes depending on which type of transfer request block you're sending, because this changes depending on whether you're sending a command, whether you're reading an event, or even if you're sending a command directly to a device or to an endpoint. So there's different types of TRBs, but they all follow this generic structure. The cycle bit that I mentioned before is the last bit of the control. This is where we write a 1 at first, and then once we go all the way around the structure, we start writing zeros. Then we care about the parameter. Depending on which type of TRB this is, we're going to want to provide some context, which is usually provided in the form of a pointer, and we put that pointer in the parameter. Then we indicate the type of transfer request block that this is in the control itself. And then there's status. So far, I've always written a 0 to the status. I do know it has a meaning, I just haven't used it. I haven't needed it so far. Finally, now that we've actually set up interrupts and we've set up a control ring and an event ring, we're ready to actually start the device. And we do that through USB command by writing a 1, which will initialize the device. So now we have our device initialized and we're ready to start sending commands and receiving events. But what exactly is this going to look like? Well, most likely the first thing that's going to happen is we're going to receive an event specifically telling us that there's been a port status change. Now, port refers to the physical port for the USB device, and status change simply indicates that some change has happened here. Either a device has connected or disconnected. I believe it can also indicate that there's been an error or the port has been reset. So it can have different meanings, but we're most likely going to read a status change when the controller starts up because a device is connected to the port. And considering we're doing this entirely in QEMU right now, we don't really have any physical ports and we don't have any physical devices, but we have told QEMU to connect a USB keyboard to the port. So most likely when the controller starts up, we will receive a port status change indicating that the device is connected. When we receive this, we will most likely want to enable a slot for it. Now, ports are the physical ports of the device, where our USB device is physically connected, or it would be if we weren't doing this in a virtual machine. But the XHCI controller actually works with slots, where each slot is assigned to a device. So the first thing we're going to want to do is enable one of these slots so we can connect the device to it. We're not actually connecting it at this point, we're just enabling one slot. So we're going to send out a command called an enable slot command, and this is where the device context space address array pointer comes in, or the DCBAAP. Honestly, the short version of it is still just as difficult to pronounce as the full version of it, so I'm just going to say this word as little as possible. But like I mentioned before, this is where we will find pointers that indicate the device context or the information about each device that is connected. And there is one per each slot. So once we send out the enable slot command, we will receive an event, which tells us that the slot has been enabled. And it will tell us the number of the slot that has been enabled. This starts with 1, not with 0. So if we receive a 0, we know it's invalid. At this point, we actually assign the device by addressing the device. That is to say, we give the device that we've just detected the slot that we've just enabled. And in so doing, we will actually allocate some memory for the device context to be written into and put the pointer to that in the DCBAAP. Again, hoping I don't have to say that word again. So at this point is where the device transfer ring comes in. Like I said before, everything we've done so far is communicating with the XHCI controller directly. But we also want to communicate with the device directly, and we want to be able to communicate with different devices separately. So we use a separate transfer ring per each device. And like I mentioned before, devices actually work through endpoints so that you can address each functionality of the device separately from each other. One example for this is, for example, a webcam that also has a microphone integrated. You want to be able to address the webcam and the microphone separately. So each of those would be put on a different endpoint. However, endpoint 0 of the device allows you to communicate with the device as a whole. So whenever I mention the device transfer ring, I'm really talking about the transfer ring for endpoint 0. By addressing the device, we're also creating this transfer ring, and that way we will be able to send commands to the device directly. But before that, of course, we need to expect the device addressed event, one that simply tells us that the address device command has been processed and has worked out, at which point we will be able to read the device context from the pointer that we put in the DCBAAP. Hey, I'm kind of getting good at saying that now. So now we're technically done sending commands to the XHCI controller for the time being, and we can communicate directly with the device at endpoint 0, which again is just communicating with the entire device. Here, we're going to want to ask the device what configuration it has and how we can configure it, and then actually do that configuration. But before we do that, we can actually request a string descriptor. Now, this is just a series of strings that give us information on the device, such as the name that the device has, the name of the manufacturer. And for example, if you want to draw a list for the user to read in order to see each device that is connected to their computer, or say enable or disable or select devices, then this is the way to do it. This will give us readable information on that. If instead all you want to do is simply identify a device by its manufacturer ID or device ID, the device context that we find in the DCBAAP will actually give us that information in a non-human readable format. But again, let's say that we want to print this information just so we have it available, just so we can maybe display it to the user, which I don't really do, but you could do it. Then we're going to want to ask for string descriptors. Different descriptors define different things, such as the manufacturer or the name. But we don't just ask for the descriptor itself. Instead, we ask for a header. That is because the header is a fixed size, whereas the descriptor can be different sizes. So we simply ask for a fixed size at the beginning. We ask for the header, and the header contains the size of the full descriptor. So we actually request it twice. The first time we request just the header. Then from that, we will read the full size of the descriptor and then request the full descriptor. Just as was the case for exFAT, these human readable strings will be in UTF-16 format, that is to say 16 bits representing one character, whereas my system currently only uses 8 bits. So again, we're going to discard half of them and hope that there wasn't any important information there, and if there was, I guess some characters are not going to be readable, but it's not a big deal. The descriptors that we really care about are the configuration descriptors. Just like before, we're going to want to request just the header, which is a fixed size, and then from the header, we're going to get the full size and request that. So let's look at this in practice to actually configure the device. For now, we're going to limit ourselves to human interface devices alone. That is to say, only devices through which the human user of the computer is going to be working with directly, such as keyboards and mouses, but not things like external drives. So first, a look at the header that I was mentioning before. This is what we're requesting when we're requesting just the header. And as you can see, the first 8 bits of the header are the length of the full descriptor. So the first time we request just this header, and the second time we use that length to request the full descriptor. And the header also tells us which descriptor type we're looking at, so we are able to parse what the information that we're reading is. Now, we're actually going to want to parse 3 different types of descriptors, the first of which has descriptor type 0x4. And this is the interface descriptor. It has a bunch of information which is definitely useful and at some point we will need to look at, but for the time being we're only going to care about the interface class, which we expect to be 0x3, which stands for HID. Like I mentioned before, we only want to support HID devices, so if we find something that's not 3 in the interface class, we're just going to ignore it for the time being. And then we care about the interface protocol, which we're expecting it to be 1 for a keyboard. Right now, we don't actually support anything other than a keyboard, and I'm actually quite enjoying controlling the system entirely with keyboard, so I'm in no rush to start working with a mouse. Although, since I did say that I am a game developer and I wanted to maybe focus on a console-like experience for this operating system, then maybe I will consider some sort of gamepad. But for the time being, we only support the keyboard, so we want to make sure that interface protocol is 1. After reading this descriptor, we care about the next one, the HID descriptor, which has descriptor type 21. Now, this one actually includes several structures, or actually we have hard-coded it to be just one, but technically it can have a lot of descriptors, which indicate different configuration types. Now, this one is a little bit special because it actually includes more descriptors inside of it, even though right now we have hard-coded it to only check for one. But specifically, we care to read about the number of descriptors that this includes, and then for each of them, we're going to want to make sure that we read a descriptor type 0x22. Now, this descriptor type technically tells us what the format that the device is going to be sending looks like. So we're supposed to parse this in order to be able to know how to parse information that the device sends us. But as is the case for a lot of other things in this system, I'm not really doing this. I'm instead just hard coding the parsing of the information that it sends me. So really, the second that we start using another slightly different keyboard, there's a chance that all of this will break. But for the time being, I guess it's fine. Once we've read the HID descriptor and its subdescriptors, we have to read the endpoint descriptor. And like I mentioned before, each device can have multiple functionalities, all of which will be put in their own endpoint. This simply describes the endpoint that we're talking about. Here we care about the endpoint address, its attributes, the packet size, which will indicate how much information we can send or receive from the device, and the interval, which, to be honest, I'm not interpreting in any way, but it is important. Because the next thing we're going to want to do is we're going to create an endpoint transfer ring, which again will allow us to send commands directly to the endpoint that we're talking to. Now, in our case, our keyboard has only one functionality, receiving input and sending it to the system. So it only has one endpoint and one of each descriptor that we've talked about so far. But like I mentioned before, there can be devices that have multiple endpoints. And each of those endpoints will have its own interface descriptor, HID descriptor, if it is an HID device, of course, and endpoint descriptor. And we're going to have to set up an endpoint transfer ring for each of them. But again, since we're just using a keyboard that has just one endpoint, then we just set up one transfer ring for that. So that's actually our third transfer ring if we think about it. The first one is the command one that we use to connect to the XHCI controller. The second one is the transfer ring for the entire device, which is really for endpoint 0 of the device. And the third one is for the endpoint that we've just discovered and configured. Well, actually, we haven't done the configuration of the device yet, so we're going to need to send up another command on the command ring called configure endpoint. And here we will set up the endpoint with all the information that we've read from here. Specifically, we care about the packet size, the attributes, the endpoint address to know which endpoint we're configuring it, and the interval, which again, I'm just reading from the descriptor and putting it into the command directly, but I'm sure it's probably important. So at this point, our device is finally configured. We should be able to receive input from the system. Again, we care about the endpoint transfer ring, which will let us communicate with the keyboard functionality of our keyboard directly. Again, it sounds a little weird because the keyboard only has keyboard functionality, but if it had other functionality as well, this will allow us to communicate specifically with the part of it that is a keyboard. And we're going to send out a TRB that simply indicates that we are requesting data. And then we're going to go to the event ring, and there we expect to find a response. Now, there is not an event ring for each device and each endpoint. We just use one event ring. Now, we can request data and then we won't receive it until the user actually presses a key, which can happen a second from now or an hour from now. We don't know exactly. This is why interrupts are particularly important. Because without interrupts, we would have to constantly poll the event ring, making sure that there isn't a new event for us to read. Whereas here, we can just continue doing what we're doing until we receive that interrupt. And when we receive the interrupt that tells us that data has been received because the user pressed a key, then we can process that data. And again, we should process this data based on the information that we find in the HID descriptor, but I'm not doing that, I'm hard coding it, and again, for the time being, it's worked. So the data looks like this. We call it a key press. And actually, we make this available to processes directly so they can interpret these key presses however they see fit. But like I said, it is based entirely on the QEMU keyboard, and I don't know what it's going to look like on another keyboard. I don't know if each keyboard uses its own different structure or not. So there's a chance I'm going to want to revisit the structure. But it indicates a modifier. Each bit of this indicates that a different modifier key, such as Control, Command, or Shift, was pressed. Then there's 8 reserved bits, and then 6 characters, or 6 keys that were pressed. This indicates that we can press up to 6 keys at the same time, and we will find the data for that in the key press structure. But let's imagine that we have 2 processes running at the same time. Do we just send it to both of them? Well, not really. Imagine that process 1 is actually asking the user for a password. Should we allow process 2 to also read that password because we're sending all input to all processes? Well, probably not. So instead, we're going to want to separate that. And also, let's imagine that we have a third process, and this process is currently not doing anything, but we want to use shortcuts to activate this process or have it do certain functionality. Well, we're going to use an input dispatch, which essentially is just going to manage input for the processes. Now, whenever we receive that interrupt that indicates that there's new input, we're going to send that input to the input dispatch. And the input dispatch is going to know which process is currently focused, simply indicating which process currently receives the input. Now, on a windowed system, which my system is not, there's currently no windows, and I don't know if I want to implement windows. I'm kind of leaning towards not wanting to implement windows, but either way, in a windowed system, there's one window that is currently focused and receives input, and that's the one that we want to send the input to. But even in my system, the current process that is on the screen is probably going to be the one that receives the input. That way we can have multiple processes running, but only one of them receives input. Now, the dispatch has functionality for setting which process is currently selected as the focused one. But this is actually not made available through syscall, which means that userland processes cannot make themselves focused. And I'm actually okay with this for the time being. I probably will need to add it at some point or another, but for the time being, it's fine because the desktop launcher, which actually creates these processes, just focuses them when it creates them and runs them. And each of the kernel level processes, such as the launcher itself or even the login screen that I showed in the last episode, are able to just focus themselves or focus the user processes that they launch, like I mentioned before. So now we have a way to set which process currently receives input, and the input dispatch will automatically send the data to that process. And what about shortcuts? Well, let's imagine that process 3 has registered a shortcut, such as, for example, when you press Ctrl R, then process 3 wants to do something. Well, in that case, if it receives this combination of keys, then it will activate process 3 instead of sending the input to process 1. But of course, this can be a little bit unsafe. Technically, you can register shortcuts to hijack the input from one process to another. So I probably need to revisit this situation and make it a little bit safer. But for the time being, I introduced a secure mode, which simply disables shortcuts. For example, this is used in the login screen so that another process cannot set up a bunch of shortcuts and read the user's password. But yeah, this entire secure mode thing needs to be revisited. I'm not sure that I want to keep it. I'm not sure how necessary it is. And I'm not sure that if it is necessary, it is enough. Finally, let's talk about the input buffer. So of course, the dispatch is going to send the input to each of the processes. But that input is going to look like this. It's going to have a buffer, which is just an array of entries, which right now is limited to 64 entries. That is, we can send 64 different key presses to the devices. But this buffer is also cyclical. So once you reach the end, you just start from the beginning again. Then it has a write index and a read index. So the write index simply indicates where the device is currently writing to, where the dispatch has currently written the last input, and the read index is the last one that the process has read. And then we have a syscall, read key, which returns a boolean if we have read a key or not, and then takes a parameter keypress pointer so that the process can allocate some space for the keypress to be written, and it will be copied from the input buffer into this pointer. So when read key is called, and there happens to be unprocessed input, then the read index will be advanced until that input is read, and the information for the latest input will be put into the keypress parameter. And the function will return a true. So that's a pretty brief overview of input. Honestly, the implementation of all that took me quite a long time to understand, but like I said before, if you want to have an in-depth explanation of this, I have linked to Flare Coding's tutorials in the description, which are much more in-depth and are actually the place that I went to in order to understand what I was doing, as well as the XHCI spec, which I've also linked in the description. But now we've actually reached a point in which this series has pretty much caught up with everything that I've done on the system. Actually, input I did quite a few weeks ago, but for example, the allocator that I mentioned briefly in the last episode, I literally wrote it mere hours before I actually recorded that episode. I also did it on a plane where the Wi-Fi wasn't working, so it may not be my best work. But hey, it seems to work just fine, so I'll keep it for now. But what this means is now I have to look forward to the future of this project. And it's a project that really I started a little over 2 months ago, so it really only took us 4 episodes to talk about the most important features that I have implemented in my operating system. And for that matter, most of them are just normal things that operating systems need to do. Like I said, I don't even fully know where I want to take this project from now on. So I asked the community about what my next steps should be, and the one with the most votes was adding networking to Redacted OS. So I'm actually working on that at the moment, and I will be posting a video on everything to do with networking for Redacted OS, although most likely, again, it's going to be a minimal implementation, as has everything else in this series been. Now, I also want to highlight a couple more suggestions that people had in the comments of that post, such as, for example, adding a tensor runtime. And I did not think this was a good idea because we're talking about embedded systems and they may not be the best place to run something like tensor. But as it turns out, tensor actually runs on the Raspberry Pi 5. So it's not entirely out of the realm of possibility, but it's not exactly a kind of project that I'm super excited about. Someone mentioned networking with a guest appearance from my therapist, and even though I took this as a joke, it actually did make me consider implementing something like Eliza, which used to be on Macs until I believe they removed support for PowerPC apps, and was just a simple rudimentary chatbot that pretended to be a therapist. And finally, people have asked in one way or another about POSIX compatibility and making my system essentially compatible with Unix-like systems such as Mac and Linux. But this will probably take a long time to do. This is more of a long-term project. So it's not entirely out of the realm of possibility that I will make it POSIX compliant, but I'm not entirely sure, and I'm definitely not in a rush to do that. So now that this series has actually more or less caught up with the actual development of the project, there's a chance that the videos will actually slow down a little bit. I have been doing weekly so far, but of course, I will also have to develop whatever I talk about in the next video. So that may take a little bit longer. I do have one video for next week, which is not actually about the development of the operating system. If anything, it's about the opposite of that. I think you can kind of tell what it is from the image, even though I blurred it. But we will be talking about that next week. Of course, I will also be working on networking, and I'm also starting to look into porting this system to work on the Raspberry Pi. Now, the Raspberry Pi actually uses an ARM processor, just like the one that I'm using, so a lot of functionality is going to be the same, but it is a different device from the Vert QEMU device that I've been using. So there's definitely a lot of adaptations that I need to make, and at the very least, I need to write new drivers for the GPU, for the networking, once I actually finish implementing the first driver for networking, for disk reading, and actually for the file system, because Raspberry Pi actually relies on the FAT32 file system, not exFAT. They should be somewhat similar, though exFAT is more advanced, so I'm kind of sad that we're not using exFAT anymore, as much as I hated it. But of course, that will require a lot of adaptations, and it's not something that I'm looking to do short term, it's something of a little bit more long-term project. For the time being though, that's all for this video. I will be posting another video next week. I'm looking into the networking video as well, maybe for the week after that. And maybe I have a couple more ideas, so stay tuned for that.